Assalamualaikum warahmatullahi wabarakatuh. My name is Mahfud Mizan and we are from Group 9, and today we are going to present to you guys some important knowledge that we need to know from our previous lab, which is power electronics. So first, what we need to know is the principal operation of the SPWM for the three-phase inverter. Okay, what is actually SPWM? SPWM, or sinusoidal pulse width modulation, is a type of carrier-based pulse width modulation. To determine output voltage, carrier-based PWM employ predefined modulation signals. The modulation signal in the sinusoidal PWM is sinusoidal, with the peak of the modulation signal always being less than the peak of the carrier signal. In sinusoidal SPWM, the amplitude of the fundamental component of the phase output can be controlled by the amplitude modulation ratio. Okay, as you can see, this is the circuit. This is the SPWM circuit that we create in order to. Okay, this is the SPWM circuit that we create to generate the switching state by combining the three sinusoidal modulation wave and the triangular scatter wave. So this SPWM will fit to this three-phase inverter.
Okay, for part 4.2b, which is I need to develop the simulation model of sinusoidal PWM for variable speed drive of three-phase induction motor using magnetic simulating. So this is the result, or this is the circuit of the sinusoidal PWM for variable speed drive of three-phase induction motor. Okay, so the output from this is this one. So as we can see, there are three sinusoidal and one V triangle, and there are three switching frequency. So yeah, this is the three switching frequency, SA, SB and SC. So this one is the V triangle, and VA, VB, VC is come from this block diagram. So for the last part, which is part 4.2c, I need to design the parameter obtained in part A. So by using the simulation model, so I need to compare whether my simulation is same or different with the result that we obtained from part A. So this is my first model of three-phase inverter using sinusoidal PWM for variable speed drive. So this is for the lower speed operation. So as we can see here, I used the 33 Hz of fundamental frequency. So the result of the speed of the motor at that time, the speed is equal to 139 RPM. So when compared to the result from part A just now, we get the same switching frequency, which is switching frequency is equal to 2.5 kHz, and the amplitude of the fundamental frequency is equal to 13.61. But the video result is 13.75. They are slightly different, but not that much. So for the high speed operation, my fundamental frequency is equal to 51, and the motor speed is equal to 161.2 RPM. So the switching frequency is equal to 1.5 kHz. It is exactly the same as what we watched from part A, but they are slightly different for the V1 or V amplitude of the fundamental frequency, which is for the video result, the V1 peak is equal to 2.1 to 1.27 compared to the simulation result. V1 peak is equal to 1.25 volt. So that's all from my part. Okay. Thank you.
Okay, at the performance improvement, what we do is we want to figure out, is it this motor can reach to the speed of 210 rpm without changing their input voltage. So what we figure out, if we increase the frequency at the SPWM side, we can see the significant increase of the motor speed. So before this, we set our frequency to 51 Hz. As we increase the frequency, the motor will become faster. And this is our output voltage spectrum for modified operation, and we get from F50 analysis. As you guys can see, a lot of harmony in this graph. As the frequency increase, the harmonic will be increased. Okay, I think that's all from us. Thank you.